All right, we're going to start out going over the homework from yesterday. So my suggestion was to start with C and write the equation first, and then you can use that in A and B. So we had a population of 24 deer introduced in 1990, and it's growing by 29%. So start with 100%, add your 29%. That gives us 129%. Move your decimal over 2, and we get 1.29. So that's going to be the base in our equation. So we're going to have y equals 24 times 1.29 raised to the x. Now we have to tell always what x and y represent. So y is our number of deer, and x, we were given a starting year in the calendar, so x is the years since 1990. Can't just say years because we're going to be subbing in like 1 for 1991. So that's the year since. You could say years after 1990 and that would be fine. In part A, we should have had y equals 24 times 1.29 raised to the first because it was 1 year after. So when you sub that in, you're going to get 30.96. This is a model that we're using to predict the deer. So the thing that best represents for a whole number of deer would be 31 deer. For 1992, we're just subbing in 2. That should give us 39.93 and change. Again, what is the model best predicting? It is best predicting 40 deer. And the last one, use your model to figure out, oops, I forgot in part C actually, it also asked to predict the number of the deer on the island today. So now we are 2021, we are 31 years after 1990. So that's y equals 24 times 1.29 to the 31st. When we do that, the nearest deer, we get 64,342 deer, which is a lot of deer. In the last one, we want to predict when will the deer be 10 times its original size. So we would want to put 240, which is 10 times the original 24, in for y. We're going to divide both sides by 24, and that'll give us 10 is equal to 1.29 raised to the x. Well, if you want to solve for x in an exponent, we want to be thinking a log. Your base is always a base. So the base of our log should match the base of our exponent. And then the base should switch what it's with. So now we're going to have 10, and then the x will be by itself. When we sub that in, we're going to get x is equal to 9.04 and change. So it asked for in which year. Well, if we were in 1990 was our starting year, 9.04 means we're going to be somewhere during that 9th year after, so it'll be 1999. So it's just a little bit into 1999, so probably in January somewhere, 1999. So today in class, we're going to be over on the next page. So this is on page 21 in the packet. So according to Planning and Economic Development Commission, traffic congestion is becoming worse every year. A study of the number of cars passing highway checkpoints in the Cape's 15 towns showed an increase of 5% each year since 1984. We're going to assume that it was going on before 1984 as well, and it'll continue. We want to know in what year will the cars passing the checkpoint double the number observed in 1984. So what we want to do here is find a time, a number of years. they didn't tell us an initial amount. So let's pick some initial amount. Let's say hypothetically there was 10 cars. So we'll have y equals 10. Off to the side, we'll do 100% plus 5% to give us 105%. Move your decimal over 2 and we get 1.05. So in this equation, x is the years since 1984, and y is the number of cars. So if we want to know when they're double, again, we just hypothetically picked 10 because if they didn't give you something, it must not matter. So double that would be 20. First thing we do, we divide the 10 over, and we'll get 2 equals 1.05 raised to the x. Well, we want to find an x that's in the exponent, so we'll do our log. The base of the log should be the base of the exponent, so 1.05. On the inside, we would have 2. When we sub that in, we end up getting 14.21. So if we take 1984 and add on 14.21, that's going to give us 1998 and change. Okay, so 1998.21. So the year during which that would occur was sometime during 1998, so 0.2-ish into the year. Well, what about when it's half the cars? Well, if we're saying we started with 10 again, we would want 5 over there. We could divide both sides by 10, and that would give us a half. Solving this would be really similar to what we did above. We'll have a log with a base of 1.05. A half is now in the inside, and we're equal to x. Well, in this case, we get x is equal to minus 14.21. So let's take our 1984 and subtract 14.21. Well, for this, we get 1969.79. So this is occurring during 1969. A common error is people will say, oh, well, it was just 14 calendar years later for the doubling, so 14 calendar years back. You got to go backwards that 0.21 and it switches the year. If you go forwards 0.21, it's still the same year. Now the last part of this, we want to show it's independent of what the initial amount of cars was. So we just randomly picked 10. What if we just left this as y equals a times 1.05 to the x? And when it doubles, that would mean we would want y to be 2a. Well, the first thing we would do is we'd divide a over, and we get 2 times 1.05 raised to the x. Notice that matches exactly what we had up here. Well, let's do the same thing for the half one. We would have a half a equals a times 1.05 raised to the x. If we divide that a over, we get a half equals 1.05 to the x. Notice that matches what we had right there. So it did not matter what you picked for the initial amount, because when you do half it or when you double it, when you divide it over, you'll end up with the same thing that we had when we just picked a random number. So to finish off your assignment for today, take the work that you copied down in your packet for this problem, take a picture of it and upload it, and that'll get you your homework credit for today. Have a great rest of your day.